We're happy to have you here and interested in IoT malware. So let's go.
Hello, my name is Andrei Costin and I'm assistant professor at University of Uvascula. What I'm doing there, I'm doing research and teaching in the field of IoT and embedded security and IoT malware. I'm also running the firmware.re project, and you can reach out to me via following contact information.
And I am Jonas Zaddach. I am malware researcher at Talos, Cisco. And I love working on IoT malware analysis, but I'm also working in general on malware analysis automation. So let's jump right into the topic. First, we're going to introduce you a bit to what IoT and IoT malware is. Then we're going to discuss the challenges that IoT malware brings with itself. We come to one of our main points, the malware study, where we look at the methodology of how we collect IoT malware and analyze it. We have an overview of the metadata we collect and survey this metadata. And we're going to present a sandbox architecture where we can analyze the samples of IoT malware. The second main point are the case studies, where we're going to present interesting cases that we found during the study. And finally, we're going to conclude, and you will have some time for questions. So, why is IoT malware different from PC malware? First, let's start with what is IoT. For us, IoT is everything that doesn't look like a computer, so it doesn't have a screen keyboard. This can be a printer, router, camera, smart light bulb, car, whatever. And why is IoT interesting for malware? So first, IoT is always on, and second, it's always connected, which is very interesting for malware if it wants to have network connectivity. Also, the awareness of malware for IoT devices is lower, and thus the defenses are also lower. Because IoT firmware usually is outdated, less sophisticated exploits are needed to bring the malware onto the device. And finally, 2 points. First, source code is available on the internet for IoT malware, so it's easy to customize it and to roll your own malware. And second, what used to be a problem, build automation, is now slowly going away because hackers, black hat hackers, have started building frameworks where you can just roll your IoT malware and have it deployed on a large number of different devices. So in IoT, we have high platform heterogeneity, different processors, different devices. We have still a low number of malware families compared to PC, where we have thousands. If you think about detection on the system, for IoT, this is very hard. You can't install a virus scanner on your Roomba, while on the PC, it's quite easy. Also, if you're an analyst and you want to analyze the IoT malware that you have found, then this is very hard because usually you will need to compile tools or you will need dedicated hardware to connect to your IoT device. Sandbox execution, again, on IoT is hard because you need a sandbox that is customized for every platform. Removal can be very easy if the malware is non-persistent. You just switch off the device and you switch it on again and you're fine. But in cases where the malware is persistent, it's almost impossible to remove from an IoT device. And finally, vulnerability assessment on an IoT device is very hard because you don't know what software is on there in the beginning. When you get the firmware, it's a bundle and you can't look inside.
Okay, before we go into the survey and take a closer look at the IoT malware, let's take a quick look at the timeline of IoT and embedded malware just to get a better context, a bigger picture. So we put this timeline just to illustrate several interesting facts. But there's definitely, like, in the middle of the screen, 2014 or 2013, there's like a interesting time point that before 2014, maybe coincidentally we related to Karna botnet and the infamous Internet Census 2012. Before that, there were cases of IoT malware or embedded malware or modem malware, but if you look at this part, it was spotty, so basically the malware was spotted or developed once every 2 or 3 years. Maybe there are reasons for that, such as it required much more skill to develop that kind of malware. At the same time, it required much more skill to detect those type of malware back then and analyze them. And also, you see that the numbers are pretty low, so they're not high numbers of malwares. Starting 2014, you can see like already IoT malware or embedded malware, call it whatever you want, starts going mainstream somehow, meaning that the number of new malware families appearing every year is high and is getting constant or even growing. And also the year is every year there are new malware families or malware IoT, malware operations, botnets, and so on. And another point is that this kind of timeline shows that still the number of IoT malware families is not so big. So it is possible to take a step back, collect all the data in an automated or manual fashion and try to see the bigger picture, where it's not quite possible so much for the PC malware because the number of samples and the number of malware family is so big. So one of the ideas was to, okay, we see that the problem is getting worse. There's so many IoT malware families and so many botnets, large botnets, abusing old vulnerabilities emerge every day almost, right? So, okay, let's take a look why this happens and let's collect all that information related to the IoT malware and understand what is the root causes which make this phenomena happen. So this is how we arrive at the idea of malware study or IoT malware study. And let's go over the methodology and the collection. So the first step was to identify the complete set of IoT embedded malware families. So roughly this set of IoT embedded malware families consists of the names you saw in the timeline earlier. Then for all these families, we identify relevant and trusted information sources such as threat intelligence reports, antivirus companies reports or analyses, intrusion detection or intrusion protection, rule sets, and we collect all this information, try to get as much metadata as possible. Then from all these sources, we just collect this comprehensive information metadata, including samples and hashes, but many researchers just focus so much on the samples and hashes and the behavior of the malware, understanding that they contain a particular vulnerability and they find its fault, but then we need more information to understand why it's happening. So we gather all the analysis and technical reports. We gather reports about honeypot logs or real-world attacks. We try to also monitor or check on reports on malware family and botnet evolution, if it grows or if it goes into a new sibling. But more importantly, we try to collect also data related to vulnerabilities and exploits and default credential lists, if applicable, to each malware family. And again, more importantly, we try to collect information on the defensive measures, because in order to defend against this IoT malware, you need good defensive measures. And it seems that the defense is lacking because there are so many devices getting into these botnets and IoT malware. So is the defense missing, or if it's present, what's the reason it's not helping? Then, of course, we collect this information, but it's mainly based on technical reports, blog posts, analysis reports, which basically take all shapes and forms, web resources, text documents, more or less structured data, PDFs. So you can see that the amount of information, the type of information is pretty diverse, heterogeneous, and it needs a bit of a structure. So we structure and systematize the information metadata so that in the future we can do these kind of surveys or measurements in more machine readable way and we can process, transform, and code based on that kind of data. Because, well, if it's in PDF, it's a nice read, but you cannot do easily too much automation on that. Then, of course, we take all that metadata, we analyze it, and the idea of analyzing the metadata, we think it can give a good report or insights in particular IoT malware specifics, but also it can help, analyzing this kind of metadata can help us understand where the IoT or embedded security fails, why it fails, and more importantly, well, understand maybe how we can give some possible ideas of how the defense can be improved in the future. Then, of course, since we also collect the metadata and the samples and the hashes, and we have binary samples, it's also a very good point to try to correlate and see whether a particular sample can be executed in a sandbox, and it really carries the specified vulnerability or CVE in the report, right? So the report may claim this malware family exploits this vulnerability. So, of course, in order to verify that claim or to verify that your protection works, it's good to run this in a sandbox and verify. We can use this analysis from sandbox to produce reports, insights, and of course, new or additional defensive mechanisms for the future. Cross-correlate all this information, and so on. So this is roughly the methodology we employed. Of course, it was developed while we went. It started like a small project, then it grew so big because we didn't expect so many resources to be analyzed, cross-checked, reviewed, so many sources of error or confusion. So a little bit about the metadata in a nutshell. We collect and cover roughly 60 families related to IoT malware. Some of them are purely IoT malware, some of them are hybrid, which, for example, target x86 but use embedded devices, CSRF or DNS changers in order to do phishing attacks. But up to date, up to this talk, right to this moment, we thoroughly analyzed 28 of them, like going in all the specific features and details we want to collect. In relation to these 60 families we cover and we collect and analyze, like in the big picture, we collected and analyzed roughly 1,300 resources, mainly URLs, leading to PDF reports, as I said, security advisory, full disclosures, vulnerability details, exploit DB, exploits, Metasploit, all kinds of resources which are related one way or another to the particular IoT malware family we analyzed. And to the whole data set of 60 malware families, IoT malware families, currently we have a collection and coverage of 120 vulnerabilities, more or less. We thoroughly analyzed the 80 vulnerabilities which relate to the 28 malware families we analyzed in depth. So we collect, analyze, review, archive the data because in many cases, some of the reports were not available anymore, or some of the defenses just were posted somewhere on the mailing list, and the mailing list is gone, and there are many cases like that. Of course, we plan to release the data set, and any improvements and corrections are always welcome through pull request. The data will be available shortly after the conference, and apologies for the delay. It will take a bit. Now, a bit about the metadata related to the malware families and to the vulnerabilities. So, related to the malware families itself, we started with a short list of features we wanted to collect, but then it starts growing. So, at the moment, we collect or try to analyze around several dozens of features. But more importantly, we try to analyze the timelines of the first seen malware sample or first seen in the wild sample, the timelines of online submission to various engines such as VirusTotal, the timelines for analysis or systematization of knowledge or technical reports, the timelines of attacks using that IoT malware. At the same time, we will also collect the information on timelines for defenses related to that IoT malware, such as IDS IPS rules, particularly tailored to that IoT malware, YARA rules, or vulnerability assessment scripts and scanners. We also collect the credential details, like the correlation of unique credentials between malwares or not. We collect the CVSS scores associated with vulnerabilities or CVEs abused by each family. Source code availability, and of course we have to keep an eye and collect the missing, incorrect, inconsistent, or confusing information which appear in different reports related to the same IoT malware. We'll go into some of these details in case studies to show that it's really not straightforward just to put all the pieces together in some cases. Then on the CVEs and vulnerabilities and exploits, we collect around a dozen of features. And basically, we are interested to see what are the CVSS scores of vulnerabilities and exploits and CVEs used by particular IoT malware families. And of course, we collect the timelines for discovery of a vulnerability, the disclosures, like private or public disclosure, the analysis timeline of a vulnerability, whether somebody is going into technical details, how the vulnerability works, whether there is any exploit or exploit proof of concept available on exploit.db or Metasploit, and whether there are any reports about the attacks using that particular CVE. Also, related to the CVE or vulnerabilities, many times it's about exploitation and the vulnerability, and not much focus is put on trying to understand the defenses behind that. So we also try to collect or correlate the defenses available for vulnerabilities and CVEs used by IoT malware, so we can know whether it's possible to protect against those vulnerabilities or not. The same thing, we keep an eye on missing, incorrect, inconsistent, or confusing information related to the vulnerability reports or to the defense rules and so on. So let's go to some numbers. We analyzed these 80 vulnerabilities. Why we say vulnerabilities or CVEs? Well, because as you can see here, from the vulnerabilities actually used by IoT malware in this subset, only 85% have a CVE, a proper CVE ID attached. So you can more or less track that vulnerability or reference to it or look it up in various databases, where around 15% of vulnerabilities have no CVE ID whatsoever. So it's really hard to cross-correlate, to cross-check. It's a random security advisory in a text document when you really need to spend a huge amount of effort to see whether this is the exactly exploit used by a particular IoT malware or not. Then, of course, by having all this information covered in these 80 vulnerabilities, we measure their CVSS version 3 and CVSS version 2. Sometimes only one is available, sometimes both. Nevertheless, they're kind of consistent. And we can see that the CVSS version 3 on average is about 8.0, 8.1. CVSS version 2 is 7.2 to 7.5. So what it basically means, it means that IoT malware is generally not it's representative, but so they generally use non-critical vulnerabilities. Okay, it's kind of expected, but they don't need to use critical vulnerabilities to be successful. So we see large-scale botnets abusing so many devices, and they are so successful, but they need to use maybe medium or high severity vulnerabilities. They don't need to go, for 0 days or so much for 0 days or so much for critical vulnerabilities. And we'll get to the 0 days or all days in a second. Then for the vulnerabilities or CVEs, normally you'd protect against them having some kind of orthogonal protections, maybe in terms of IDS, IPS, and maybe regularly scanning your devices or network using vulnerability assessment systems like OpenVAS or Nessus. In this kind of system, it's IDS, so it's more examples of IDS, Snort, Suricata, and other types of systems. And we saw that only, in this set of 80, only 53 we could find, for 53 of these vulnerabilities or CVEs, we could find an IDS rule. Whether it's in public sources or private sources, it makes a small difference, but the idea is that whether there is a rule protecting against this vulnerability or not. And the interesting thing is that by analyzing the timeline of disclosing or releasing these IDS rules, the trend is that on average there's 184 days delay between the knowledge about the vulnerability, meaning disclosure or exploit or proof of concept, and the IDS rule itself. So it's about half a year delay. Of course, it's statistically spread, but it's a half-year delay between a particular vulnerability and the potential to defend against it. So it's a bit, well, we can improve that maybe, the way the defense rules are released, and we'll get to that into the key takeaways, but a hint could be maybe when releasing the full disclosure and exploits, release also the IDS rule with it, like as part of the disclosure.
Something that you can also see in the huge difference between the mean and the median is that there are a lot of cases where it is covered below the 184 days, but then there is a number where the time to coverage is very huge.
Yeah, so it could be explained, we didn't look so deep into that, but it could be explained that before 2014 or 15, the security and the defense and the vulnerability disclosure processes were not so well streamlined, not so well standardized, so it looked a ridiculous amount of time to get some defense rules or to get all the things rolling. So now we can see that there's a shift, like a slow shift towards streamlining the operation, but still there's some delay, which can be improved, of course. On the vulnerability assessment rules, again, examples Nessus or OpenVAS from Greenbone, we could find only 33. Maybe it doesn't mean that the others are not present, it's just we couldn't find them in open source using the CVE identifiers, the payload samples, or other relevant information to the vulnerability. And based on this, analyzing the timelines again of releasing these rules for these 33 vulnerabilities which have VAS rules, we could see that there's also a delay, not so significant as for IDS or IPS, but still there's a delay in releasing the assessment scripts. So roughly there's 2-month delay before you can actually assess your devices whether they're vulnerable or not. Of course, you can write your own scripts immediately after knowing about vulnerability, but there are like tons of vulnerability being released every day. You are not keeping an eye on that. You are using some automation tool, and most likely it will come with 2 months delay to your system. So you might not know that your devices are vulnerable to that particular vulnerability. Then on the malware families, it gets a bit more complicated, because for malware families, there could be defense rules which are specific to the malware family, but then we can analyze this separately or then augment with defense mechanisms of the vulnerabilities which are related to the IoT malware, right? So from these 28 malware families we thoroughly analyzed up to this date, in general, the idea is that most of them use around 3 vulnerabilities or CVEs as part of their operation. Of course, there are outliers which use 1 or 2 or 3 dozens, like BrickerBot or VPN filter or exploit kit DNS changer. They use several dozens, but in general, the trend is about 3 vulnerabilities, and it's enough for a very successful IoT malware or botnet operation. And this also includes the generic CVE or generic vulnerability of default credential scanning. So some of them just use one type of vulnerability, which is default credential scanning. And the interesting thing is that if we augment the timelines of CVEs and vulnerabilities with the malware where they are being used, we can see that the knowledge about the CVE and the vulnerability, therefore the possibility to defend against them or to protect against the malware abusing these vulnerabilities, was in general available 790 days before the malware starting using those vulnerabilities, meaning that there's roughly 2 years opportunity window to actually address those vulnerabilities, but still after 2 years the IoT malware can go and easily abuse them. Of course, we try to look whether there's some IDS or IPS rules particularly tailored to the IoT malware family or to the payloads of the IoT malware families or the CNC communication channels. And we found from the 28, only 17 we found having these specifically tailored IDS rules. And in general, these IDS rules for the malware family, you can see that they come generally 81 days after the knowledge about IoT malware, that particular family is known. So it's an improvement compared to the CVEs, meaning that for the CVEs, the IDS knowledge comes 200 something days. Here is 81 days. Is good, but at the same time, if we take a different perspective and augment the IDS data from the vulnerabilities into each malware family, we can see that IDS protection for the vulnerabilities abused by the IoT malware families were available around 700 days before the IoT malware hit. Again, like there was like 2-year opportunity to use those defenses some way or another, but we don't know yet why it didn't happen or why it's not happening. Maybe it's not streamlined, maybe there's some security gap we need to understand. That's an open question, that's part of a, maybe human interview, or I don't know. Then we do the same for vulnerability assessment rules. These vulnerability assessment rules like Nessus or OpenVAS scanners, they are mainly tailored in verifying where a system or a device is vulnerable, so they are not particularly tailored to verify if a malware is vulnerable, which could be an interesting study, but still. So there's only one rule, and well, it also comes later. But the interesting thing is that if we augment the VAS rules from the vulnerabilities and CVEs, then kind of we have the same consistent picture that there's around 700 something, like 2 years and a bit, that vulnerability assessment rules were available for the devices affected by those IoT malware. So there was plenty of time to scan the network or to scan the ecosystem and eventually figure out that it's possible to be vulnerable, but for some reason nobody scanned, or maybe they scanned but didn't patch or didn't install IDS and IPS, and then the IoT malware 2 years later, after the defense is available, still can create a botnet. The same for YARA rules. YARA rules, they do not usually apply to the CVEs, but well, it's more like a forensic defense mechanism, and we can see that only 11 have YARA rules specifically tailored to IoT malware, and they also come with a certain delay. So it takes some time to use those rules to understand if a compromise happened on a device or not.
Okay, then we come to the part of the dynamic analysis. So after having collected the samples, we also wanted to extract some indicators of compromise by running the samples. And the problem here is that in vivo analysis is very challenging. If you want to analyze the malware in its environment, you need to build tools for every device. So you need to compile GDB or strace to gather syscalls. And if you want to go even deeper, then you will do in-circuit analysis with a JTAG device. But this is non-trivial. It requires lots of knowledge. It requires knowing the registers of the CPU and so on. So it is very time-consuming. So if we want to go in a way where we can analyze a high volume of samples, we need to automate that. The challenges in automating that is that the heterogeneity of the platforms for IoT is huge. There are different CPU architectures, there are different runtime libraries like on Linux glibc and uclibc, and they're incompatible, so you cannot install them on the same system. You have special CPU instructions, like on ARM you have the coprocessor instruction, where you can access device-specific registers, and on all IoT devices everybody can implement their own registers. If you get over this point, then you still have a high preparatory work. You need to prepare a tool chain for every architecture that you want to analyze. You will need to build system images with a runnable Linux. And finally, you need instrumentation so that when you run the malware inside the system image, you will get useful information. And once you have reached that stage, the problem is that the tools that you use are little tested. So, for example, they have been tested for x86, but not for ARM. And you will need to write patches for the code to compile in the first place. And then afterwards, you will encounter a lot of bugs. So to visualize, again, the platform heterogeneity, here a bit opportunistic example. On Windows x86, there are two types of binaries I can have, x86 64 and x86. But even if I run an x86 on an x86 64, I'm fine because there's emulation for that. If I want to run an IoT binary, then of course first there are different operating systems. We are only interested in Linux. On Linux, the binary can be statically linked or dynamically linked against glibc, uclibc, and musl. And as I said before, for each of those you need a different system image. Then the binary can be for different processor architectures, ARM, PowerPC, MIPS, x86, or something else. And inside one of those architectures, you can have MIPS revision 2 and revision 6, which are mutually incompatible. So again, you need one image per revision. And you cannot run a binary for one revision on the other. And because this is not enough, there's also endianness. So the binary can be little endian or big endian. And you need, again, a new image for both of them. Okay, so there has already been some attempts to run IoT malware in sandboxes. Most notably, there is Costin et al., who grabbed a huge number of ELF binaries from VirusTotal and executed them and gathered results. There is also the effort by Hunting Malware. The link was working this morning. Sometimes it's down. This is an effort of Spanish researchers, and it is very similar to our approach. It's based on Cuckoo. There is Limon, which is a sandbox based on strace and Sysdig, but it has only limited support for non-x86 architectures. And finally, there's Detax, which has support for other architectures, but hasn't been touched in the last 2 years. So our architecture is based on Cuckoo mainly. It is wrapped in Docker for ease of deployment. And the huge contribution that we bring is the build-root environment, where build-root is a package-less Linux distribution. So this container will build the system image that is afterwards used inside the QEMU emulator. The QEMU emulator can emulate all the different CPU architectures on x86. And we instrument the image that has been built with systemtab, so that we know what's going on inside when we execute. So the system image is compiled with build-root. We just need to give build-root a distribution configuration, which tells it which packages to install inside the system. We need to give it a kernel configuration so that the Linux kernel can run on the QEMU device that is being emulated. And we need to supply it with additional patches so that everything works. And build-root is very handy because you can add build hooks, and we can build our instrumentation with a build hook before the actual image is built. So the analysis process is that the sample is triage. So for example, if you have an ARM sample, it is associated with an ARM image. Then the emulator is prepared, the systemtab script is loaded, the sample is injected, the sample is executed. Once the execution terminates, either because the sample finished or because there is a timeout, then the log files are retrieved and Cuckoo parses the log files. And this will give an example report like this here, where you can see the syscalls that are happening inside the sample. So here I have, this is the normal interface of Cuckoo. And if I want to upload the sample, I can simply use the web interface. The only thing that I will do different from a normal execution of Cuckoo is that down here I will choose package generic, and I will choose my machine, which is my ARM emulator. And then I can go to analyze, and the sample will analyze in the background. I have prepared two analyses that I've done before. One is of a VPN filter sample. So you can see here that the sample starts several processes. And what is typical for VPN filter is that one process will try to close all the file descriptors before. And you can see that here, a lot of them are closed. Another sample that I have is Bashlight, which is an old Linux malware. You can see here that it claims to be SSHD, which is of course not what it is. And it connects to the Google name server, and it tries to read ProcNet route to find out what the routing table is. Okay, so let's go back to presentation mode and over to Andrei for the case studies.
Okay, so some of the case studies, well, based on so much data, you can build so many case studies, and we have a bunch of them. Depending on the time, we'll show all of them, we'll just skip through some of them, but it's interesting to look at some challenges associated with doing such kind of manual analysis, correlation, review, correction, etc., etc. So the one interesting case study, which I personally find interesting, is the Hydra D-Link exploit. So Hydra is a very well-known malware. It dates back to 2008, at least the public knowledge says so. It is known to abuse authentication bypass vulnerability in D-Link router, and luckily the Hydra code was open source or leaked in April 2011, so we can see a screenshot of it. So basically it's written in C, not, well, it was at that time chosen to be so. What it does, it basically retrieves the unauthenticated access to a configuration page. You can see that it grabs for passwords tag. So basically you can see these opening and closing HTML or XML tags. So this configuration page just returns unauthenticated the password in these tags, and this Hydra malware just parses the tag, gets the password, and can have basically root admin credential on the affected devices. Again, interesting, well, it makes sense that the malware would not open a CVE for that and will just abuse the exploit, but this knowledge is pretty old, it's more than 10 years, and there is no CVE associated, at least I couldn't easily find or couldn't find at all any CVE associated with this particular exploit even after 10 years. Fast forward 5 years, there is a very nice researcher doing very interesting stuff also on embedded devices, rediscovers the same, similar, very much related vulnerability, related also to D-Link routers, just different firmware version. It's again about authentication bypass, fetching the configuration file, and so on. But basically it's the same vulnerability in a nutshell. It's 5 years after the Hydra abusing it, and still there is no CVE associated to it. Fast forward 4 years, so basically very recently, IoT Ripper has been spotted in 2017 to abuse this vulnerability. There's also even a Metasploit module. Maybe it's too small, I don't know, but if you download the slides, it will be visible. Metasploit does the same, grabs for password tag, downloads gets the password, and accomplishes successful exploitation. And then shortly after Reaper, or at the same time with Reaper, there are two different independent security companies doing research, and they find different set of D-Link devices basically having the same kind of vulnerability, unauthenticated information disclosure, meaning the admin credentials, and still CVE map no match. There is no CVE. So you can imagine that there is duplicated work. There is a lot of confusion whether it's the same vulnerability or not when there is no CVE attached. It's really hard to track and figure out all that information. Is it the same or is it not? Is it used by the same malware, and etc., etc. So it's a challenge in itself. So there are many open questions. I'll not go into them, but the idea is that why it takes so long until a CVE should be associated even in retrospect to a very well-known and exploited vulnerability. But it's more like an open question, how can we improve this vulnerability disclosure, vulnerability management processes. Another interesting case study is what we call VirusTotals in the wild. I think many of you use VirusTotal. So one of the interesting features in there is for some samples, not for all, they have a field called first seen in the wild. And it looks really interesting, like, whoa, you can see when this sample was first seen in the wild, and you can establish a timeline when this exploit was developed and so on. So it gives you a lot of features. However, reality is a bit different, and we found at least 10 different malware families that have first seen in the wild strangely set to the same date. So basically, it doesn't make any sense that unrelated IoT malware would have the same first seen in the wild, exactly the same date. And moreover, some of these samples were pretty recent, like 2000, or they were discovered and analyzed or developed pretty recently, 2018, 2016, and basically doesn't make sense. There's no time travel. Doesn't make sense that they would be like in the wild in 2010, exactly on the same date. We follow up this with VirusTotal. They were kind enough to explain. And basically what it boils down to is that because of how they gather the threat intelligence, sometimes it's fairly easy to fake this first seen in the wild or perhaps some other information. So they would advise not to take it like, as a ultimate truth that this is the first seen in the wild. So basically you could have a zip file with timestamps dated back, and all the sample, boom, become 1970, first seen in the wild. So the conclusion, not all metadata is created equal. You need to trust your metadata vendor, but at the same time, if VirusTotal is de facto standard, everybody uses it, enterprise or community edition, like you trust it. And in this case, if you cannot trust that, what should be like the ultimate source of information? But again, another question, not necessarily to VirusTotal, is like to the community. How can we derive or follow up on that kind of information? Then there's a lot of challenges with metadata analysis. One example is the missing CVE numbers, which we often see. Well, this Hydra doesn't have a CVE number, so it makes sense. But then there are other examples which are more recent. For example, for Hajime, it says that it is using the password of the day backdoor. This password of the day backdoor has a particular CVE number. Why not having this information in the report in the first place to make the analysis or correlation or machine learning, whatever you want to do, like having all the information without having any confusion in the first place. Then there's wrong CVE numbers. For example, the Moon worm from 2009. It used to exploit a Linksys vulnerability, which doesn't have a CVE number, but goes by this exploit DB ID. However, in some intrusion detection system, this pops up as alert 2012-1823, which is totally unrelated. Then another example is the messy CVE numbers, what I call them messy, meaning that they relate to the same malware family or to the same CVE, but all the information is contradictory or is like utterly confusing. So VPN filter CVE number 2013-2679, Trend Micro, they do good analysis. They mention OS command injection for Linksys device. If you go to the exploit DB or to the reporter of this vulnerability, the same vulnerability is stated as cross-site scripting reflected, so there is no relation to that. Even worse, if you go to Mitri, who is managing the CVE database, it says reserved. So it means that there is no clear picture on that vulnerability, and it's just getting more and more confusing. What this malware is exactly using, which CVE number, which vulnerability, which IDS should I enable, which rule should I deploy in order to protect. Then of course, sometimes you can have, for example, IDS rules, but because the same IoT malware family goes by so many different names depending on the threat intelligence on antivirus company, sometimes you find it as Zollard in some rule set. In some other cases, you find it as Dart laws. So basically, you need to know the whole name set for a given malware in order to be able to find correct IDS or defense mechanism. It's not just going, punching the CVE number, and you get the defense out of the box. It's kind of a tedious process. So, coming to the conclusion. So, we have several key takeaways. One of them is to understand IoT malware. We think that a wider view is both necessary and beneficial. So, we must go beyond just looking at the sample, bare sample, and analyzing the behavior. We think that we must widely and intensively use metadata, timestamps, timelines, security advisories, whether they're CVE or not CVE registered. Basically do what we did for the past couple of months, do internet dumpster diving. It's really internet dumpster diving because some of this information is like hard to grasp. Another key takeaway is to improve security posture of IoT or embedded devices. We think that proper vulnerability management, disclosure, and defense, I think everybody thinks this, but in practice it somehow doesn't still work like 100%. So we need to dramatically improve the CVE and disclosure management, And well, some possible solutions could be integrate the defense part as part of a full or responsible disclosure. So when you release the analysis of a vulnerability, or you release the exploit or proof of concept, release the defense part of it as well, or even before that, release the defense part. So at least the sysadmins, the interested users can deploy the defense before the exploit is picked up by the malware actors and so on. Maybe having some kind of bug bounties for defense, identify the critical CVEs or vulnerabilities which do not have any defense mechanism in rule sets and so on, and just bug bounty them so that students or whoever is interested would earn some money and also will develop some useful defense mechanism. And maybe also, as a community, maybe we can do security data cleanup day challenges where we go over these sources of information on exploit DV, CVE, emerging threat, and just keep updating the data, clean it up so that we can come to this key takeaway, that in order to enable AI-powered cybersecurity, everybody wants that, but in order to reach that, we need proper, clean, structured, updated data is absolutely necessary. Otherwise, we just go to what is like commonly known as GIGO effect, garbage in, garbage out. You cannot have a proper AI cybersecurity for IoT malware or whatever when your data is so confusing or incorrect or missing key information.
Yeah, that's kind of it. So what we want is we want more and better tools. We hope that this research inspires others to continue and open some and close some of the open questions here, and that we help you.
Thank you for your patience. We are open to Q&A. I think we have like 4 minutes. Here are contact information. We will make sure that the tools, the data set and the updated slides and white paper is there. We are open for questions. Thank you.